All right, we have a soda can problem, and basically a soda can is a cylinder. So there's our can. Cylinder is defined by its height and radius. So there's our picture, and the information given in the problem is that the volume is 26 cubic inches. Volume of a cylinder is the area of its base, which is pi r squared times its height. So pi r squared h equals 26 cubic inches. We want to minimize the amount of aluminum needed to make this can. In other words, we want to minimize surface area. So the surface area of this thing, you can think of the top and the bottom, of course, 2 pi r squared. Those are circles. But what's the area of the side of the can? Think of taking that side, cutting it, and unrolling it. You get a rectangle if you do that. And the area of that rectangle is the circumference of the base, 2 pi r, times the height. Those are the length and the width of the rectangle you would get if you unrolled this can. So we have a function that we want to minimize. We call that the objective function. So we want to minimize this objective function. We know how to minimize things, right? We minimize with derivatives. But SA is in terms of two variables, h and r. So we've got a surface area. We have a function we want to minimize, but it's in terms of two variables. This is single variable calculus. We have dealt with functions of one variable and taking derivatives and optimizing functions of one variable. And now we have a function of two variables, and that is where the volume comes into play. So the volume comes into play here. We can, from the volume equation, from the equation for the volume, we have h equals 26 over pi r squared. So we have h in terms of r, right? That's what this is. This is h in terms of r. We can plug that in to the surface area equation, and we can get that the surface area, let's just write area as a function of r, is 2 pi r squared, the area of the base, the top and the bottom, plus 2 pi r times h, which is 26 over pi r squared. So this area is now just a function of one variable. We've eliminated the h. We use the extra information that the problem gave us, namely the volume, and we use that to eliminate one of the variables, in this case h. And we suppose we could have used it to eliminate r, but that would have been harder because in the volume equation r is squared. So we chose to solve for h and eliminate h. So that's our area as a function of the radius. Let's cancel the pi's and cancel one of the r's and get 52 over r. So that's the function. It's a function of one variable. Now, at this point, we've done everything that's new in this section. At this point, we just have an optimization problem, just like in the other sections that we've done in Chapter 4. So there's nothing new at this point. We take a derivative where we know that the max and the min will occur at an endpoint or at a critical point. So we want to find the critical points. A prime is 4 pi r minus 52 over r squared. And remember, to do the derivative of 52 over r, we can write that as 52r to the minus 1, and then use the power rule on that. So we have the derivative. We want to know where the derivative is equal to 0. Those are the critical points. So we set that equal to 0. We have 4 pi r equals 52 over r squared, or r cubed equals 52 over 4 pi. So r is the cube root of 52 over 4 pi, which comes out to be 4.14 inches. So that is the critical point here. That is where this function could have a local max or a local min. Now we can determine whether this is a local max or a local min by using either the first derivative test or the second derivative test. I can pick something to the left of 4 inches and plug it in to a prime here to see the sign, to see if the function is increasing to that point or decreasing. Or we could use the second derivative test. If we use the second derivative test, a double prime is 4 pi plus 104 over r cubed. So a double prime of 4.14, the second derivative at our critical point is positive, which means we have, which means it's concave up at that point, which means we have a local minimum. So corresponds to a local minimum. That's the second derivative test. So we have a minimum. We wanted a minimum. That's good news. We've got our minimum. In this case, there are really no endpoints to check. We could have r equals 0, but that would mean an infinitely thin soda can that's infinitely tall. It doesn't make any sense. You know, we could have some other extreme where h is 0 and the infinitely fat soda can that has no height to it. So there's no real endpoints in this problem, which means this local minimum has to be our absolute minimum. So that is our minimum. That's the dimension that works. So r equals 4.14 gives us our minimum. The height is, we have height in terms of radius back from the volume equation. So the height is going to be 26 over pi times 4.14 squared. And that's our solution. It asks for the dimensions that minimize the amount of aluminum. We found the minimum using calculus, and that's our answer. If you actually look at those dimensions, plug in these numbers for h, you'll see that soda cans are not designed this way at all. All right, the optimum here gives us soda can that's more like a bowl. It's really wide and really short, but that is how you would minimize the amount of aluminum needed in this process. So obviously, this is not the process that Coca-Cola goes through. This is a good example of these types of problems. We have to come up with the function that we're minimizing, the objective function. Usually there's some other information given in the problem to help us deal with the objective function, to reduce the objective function to a function of just one variable. Once we have the function as a function of one variable, then it's just calculus. Then we go back to finding the critical point and seeing if we have a local max or local min.